Hello everyone and welcome to another episode of The Hidden Quantum Champions. In today's video we are going to look at ParityQC, and without further ado, let's dive right into it. So here we are at the website of ParityQC. It says the Quantum Architecture Company. And we have an arrow down here. So let's start to scroll. ParityQC is the world's only quantum architecture company. We develop blueprints and an operating system for highly scalable quantum computers with applications ranging from solving optimization problems on NISQ devices to general purpose error-corrected quantum computing. The ParityQC architecture introduces a paradigm shift in the design and creation of quantum computers that are powerful, scalable, and flexible. ParityQC's operating system, ParityOS, provides access to all the advantages of our architecture via the cloud. Our co-developed approach to hardware and software results in quantum chips and algorithms that fit together perfectly. So there's a lot of information in that. Let's go through it step by step and disentangle. So they are a quantum architecture company, which means they don't have their own product as far as I understand, but well, they do have their own product, which is ParityOS and the ParityQC architecture, but it's like their customers are quantum computing manufacturers. So they are selling architectural components to companies that are trying to build quantum computers. That's also what it says here. We develop blueprints and an operating system for highly scalable quantum computers. So blueprints as in probably chip layouts for specific types of chips, and I guess we will learn about that as we go through their web page. And then there's also an operating system, so also on the software side. Kind of like in the classical world, we have these offices that, for example, do ASIC designs, so very specific electronic integrated circuit designs for specific types of applications, and then they sell this IP to the chip manufacturers that then, I don't know, use that to build their own chip for a specific application, like, I don't know, automotive cameras or whatever. So looks like we have something like this here. Then we also have this NISQ in here. So these are like the current types of devices that we have. So kind of the non-error corrected qubits that still produce some errors when you run them. That's what this NISQ is. And then as things are moving forward, there's also here the error corrected quantum computing. Okay, so let's go down. We see some geometrical shapes here, which I guess matches nice the idea of the architectural point of view. So here it says real-world problems. Quantum computers will be able to solve specific industry-relevant problems much faster compared to classical computers. Hence, that at least the promise, right? One example is optimization problems. We are ubiquitous in the real-world world, which are ubiquitous in the real world, from healthcare to finance, manufacturing to logistics. They are complex and intrinsically hard to solve. Okay. Then we have translation to quantum computers. Due to their complexity, real-world problems require a large number of qubits when encoding them on a quantum computer. In the standard approach, these problems are either encoded directly into the hardware or in gates between qubits. This results in complex chip layouts and large systems. And so first of all, very nice website with all these geometrical shapes. I like it. It's kind of a mix. It's a bit like a pitch deck, right? You're scrolling like through the different slides where it kind of guides you through the story, I guess, of the value proposition of what ParityQC is offering. Quick point on this here. So this is kind of differentiating between two different approaches towards quantum technology. So on one hand, you have like the specifically optimized chips that are going to solve one specific problem, right? Like, for example, you have this annealing systems. D-Wave is a famous company in that space. These ones, they are very specifically made to do this type of annealing task, which maps to specific type of problems, optimization problems. On the other hand, we have here this gate-based approach where you have the qubit. So it's like the quantum analogon to the classical bit. And in the classical compute world, you have specific gates. So these are operations that you can apply between two bits in order to do some types of calculations. It's like an AND gate and an OR gate, and like negation gate, which kind of turns a 0 to a 1 and a 1 to 0, things like this, right? And in the same way, in the quantum world, there are also these types of gates that kind of apply to a single qubit or to multiple qubits. So an example is, for example, the Hadamard gate. But that's just a side story. So these are two different approaches. These gate-based quantum computers, they can actually operate on a much larger number of problems because they are basically like general purpose compute architectures for these quantum computing tasks. So maybe not only optimization problems, but you can also use them to emulate, atoms. Okay, next, geometrical shape. Reduced complexity and simplified control. The ParityQC architecture separates the problem from the hardware through a revolutionary and highly scalable design in which the same chip can solve any type of problem. Its structure is simple and parallelizable, ensuring ease of scalability and full programmability, and it has an intrinsic error correction potential. It provides benefits for every current available 2D hardware platform and for both digital and analog methods. So now here we say 2D hardware platform. So I guess this is like two-dimensional layouts, so chip layouts of qubits. And then it says something here, digital and analog methods. And if you want to learn more about that, maybe also go back and check out the other videos, because there were some, like for example, in the neutral atom world, there were some digital versus analog discussions involved there as well. Okay, nice animation here. There it goes onto the chip, and then it says combined approach, hardware and software working in parity. That probably hence the name ParityQC, right? The key of a perfectly aligned quantum computer is the simultaneous development of hardware and software. This approach will ensure we achieve quantum advantage in near term. By adopting our unique architecture together with ParityOS, hardware developers benefit from years of research in a complete package that offers a simple blueprint for quantum chips and operating system that is easy to implement. One thing that maybe is interesting to point out here is this wording about the quantum advantage. The quantum advantage is basically a wording to describe that you can use quantum computers to solve problems that classical computers cannot solve. What do we mean by that? Well, actually, you can also solve them on a classical computer, but the runtime of this algorithm will actually take so long that it's not really practical. So, for example, in some cases, you might say you want to create a problem on the quantum computer and execute it there, and the execution on a classical computer of that very same problem would take as long as we think the universe is old. So then you could say, okay, this is not practical because you cannot wait for the lifetime of the universe for this to be computed, right? So that's like this idea of quantum advantage. And of course, there is like academic problems, and there have already been several approaches by different companies to do that. I think the first one was probably, I think the first one to look into that might have been Google, to say something, and an IBM later on, I think, showed that, okay, you can, if you do the right approximations or if you use the right methods, you can maybe also do it quicker, or maybe it was vice versa. I don't remember the details. Don't pin me on the details. But this is like all, let's say, academic problems. And there's also the real world problems, right? That are the ones that are relevant because we want to build a tool that we can use in real world. And there, I think at this point in time, there are a couple of claims out there where people say, okay, we've reached this. We have shown that like for a specific type of application, a quantum computer is better or has an advantage versus a classical computer. However, there's also still some debate if in these different claims this is actually something that is being reached. And I think it's also kind of hard to tell because on the one hand we have the academic metrics, as in like, I don't know, how many iterations does it take to solve that problem. Then you could maybe also say, is it more efficient in terms of energy utilization, or I don't know, there's like several different metrics. And if you really look into it in the detail, I think it's not so easy to actually say at which point is quantum advantages actually reached, because you would need to have something that is like orders of magnitude better than what a classical computer can produce in order to really show this difference. Like when they are kind of on pair on something, or if there's only like a little advantage, I think it's hard to show, because like classical computers, they're also still developing. There's new hardware coming every day, specialized hardware for specialized tasks like GPUs, AI accelerators, all of that stuff. So it's kind of hard to say where like the limit of classical computing is reached and where like a quantum computer can actually add in terms of capability, at least from my point of view. Maybe there are people who have different opinions. Please, let's discuss down in the comments below. I'd be very interested in hearing your opinion on that. Let's scroll down a little bit further. Here it says performance with ParityOS, solve real-world problems with simpler and smaller chips. So I think here it's, let's say, a little bit explained a little bit more in detail. So ParityNS enabled hardware developers and users to skip the spin modeled presentation and encode industry relevant problems directly along with multiple variable correlations and side conditions. This introduces a new way of approaching industry relevant problems with higher order constraint binary optimization, HCBO. HCBO is, I think, an interesting class of problems, and I think we will definitely, I think we will do some tutorial series, or let's say some more academic series on this topic in the future on this channel. So if you want to learn more about it, if this is interesting to you, make sure to subscribe so you don't miss out on this. Now let's take a look at this graph here. So it says quality of approximation. So here we're talking about approximation problems, and here we see number of quantum gates, ParityOS and architecture performance and quantum chemistry, ground state calculation of lithium hydride molecule. So I guess that's like I would guess that's like a relevant molecule for battery chemistry, because it's lithium. And then you see here like the number of quantum gates, which goes up. Here you see the quality of the approximation. In order to do a good simulation, you want to approximate as close as possible. And for this, now we have these different lines here. So we see the standard compiler and standard hardware, which kind of scales, I don't know, maybe it's quadratic, maybe it's exponential, but you can see it rises up quite quickly. As you go up in the quality, actually the gates, they're going up quite quickly. Now here we see ParityOS with standard hardware, so that's like their operating system, which I guess is like a quantum inspired approach, but still on normal hardware. So like standard as in non-quantum hardware, I guess, maybe GPUs or CPUs. You can see this is already like much better in performance than the other one. And then here the last one, the red row, is like ParityOS plus hardware based on ParityQC architecture. So that's probably now some quantum type of hardware, I would guess. And that's like the lowest line here. Okay, so that means it performs best, right? And not just a little better, but really a lot better than the other ones. Okay. Software and hardware and parity. Here we see a couple of trusted customers, I guess. There's DLR, there's Planck, there's Electron. So research organizations, but also companies from the quantum space that are using these services of ParityQC. Then we also see NXP, which is quite a big silicon player here in Europe. Quantum Brilliance. So there's other companies in there as well. We see they are based in Austria and Germany, hence the GmbH here. And there are also some funding initiatives by Austria and Germany, among others. Okay, so let's very quickly check out the architecture tab and see what they're telling us here. So we see some pictures, reduced complexity, on chip for every problem, one chip for every problem, all methods and platforms, scalability through parallelizability, qubit control, error correction. Okay, so and a lot of text, which I will not go through for now because time's flying, right? Then also quickly check out the ParityOS here. We created ParityOS with the aim to offer an all-in-one solution to solve real-world problems on quantum computers. We see here the real-world problem going through ParityOS, and at the end what comes out is a quantum algorithm and quantum and hardware design as an output. Okay, so if I understand this correctly, and I mean correct me if I'm wrong, what I'm getting now is, so you have the problem. If I understand this picture correctly, you have a specific problem, like an optimization problem. You want to solve that. You basically encode this in ParityOS, and what it will give you is, it will give you a hardware that you can use to actually solve specifically this problem. So it will spit you out, I don't know, a chip design, and this chip can at the end be used to solve this specific problem. But maybe I'm also wrong. Maybe I'm understanding this wrong. So we have accessible, simple interface and easy to use, always available, the quantum operating system in the cloud, fully parallelizable, the key to scale and efficient to scalable and efficient algorithms, the next generation compiler. So I mean, that would also kind of match that we have a compiler, right? Our aim with ParityOS is to provide the compiler for the next generation of quantum devices. When building a quantum computer based on ParityQC architecture, hardware developers also receive the full software stack for using the architecture efficiently. End users and academics can make use of ParityOS to develop algorithms for next generation quantum computers for applications that range from quantum chemistry, material science, machine learning to financial optimization. Okay. With that, let's quickly also check out the news session here on the page. I'm recording this end of August, and what we see here, I think there's no timestamp on here. Maybe let's quickly open this one just to see. So this is from end of August, so second half of August. So this is pretty much up to date. We see there's like awards, insights, news, papers. So there's like something that is more probably general in the news section. Then we also have something here on the academic side of things. I guess these ones, they are more like on the basics, parity principles. Okay, no, that's like maybe some people from the company that explain, right? There's like a video overview here, ParityOS. So I guess that's like explanations of what they're actually doing. So if you want to learn more, go check it out. I guess that's interesting. And then there's also something here about working in the company, where I guess you can learn a little bit more about like how the working conditions are and what jobs they actually have. With that, I think we are already done for today's video. If you liked it, please make sure to give it a like. And if you don't want to miss out on the next one, then make sure to subscribe to this video. As always, please stay hydrated, and then see you in the next one. Bye bye.